Now, we have defined the transfer function to be the ratio of a specific output of the linear network over the input to that linear network. Now, in general, we can express the transfer function as a ratio of two phasors, n of omega and d of omega, where these two phasors may not be necessarily um, equal to the output and the input respectively. Now, we can get roots of, so given an n of omega, we can actually get the roots of that phasor when we equate that to zero. So if we equate that to zero, we will get several values for j omega, such as z1, z2, and so on. Now we call those roots zeros of the transfer function. In the same manner, we can also get the roots for d of omega if we equate d of omega to zero, and we'll get there j of omega equals p1, p2, and so on. Now these roots are called the poles of the transfer function. Now the roots of n of omega are called zeros because if we substitute the value of those roots to n of omega, we'll get a zero transfer function. On the other hand, if we substitute a pole to d of omega, we'll get a transfer function that is infinity. Now, in our succeeding analysis, it would be convenient to let j omega equals s, as we'll see in next example. So let's have another example. Let's say we have this circuit where output is taken across the 0.2 farad capacitor. So in here we are asked to determine the transfer function. Also, what are the zeros and poles of the transfer function, and then the frequency response. So in C, we will be plotting the magnitude and the phase of the transfer function that we get from A. Now we can solve this, or we can solve the transfer function using mesh analysis. So let's say we assume mesh currents I sub A and I sub B. So we let first j omega equals s, then we develop the equation for mesh A. So this is the equation. Standard circuit analysis. And simplifying this, you'll get this simplified equation. So let's call this equation 1. Doing the same for loop B. So we'll have this equation, and simplifying, you will get this simplified equation. We call it equation 2. Now simultaneously solving the two equations and solving for I sub B, you will get I sub B equals this one. So I sub B is a function of B sub I. Now take note that the output would be the impedance of 0.2 F, so that will be 1 over 0.2 S times the current that is flowing through this capacitor, which is the mesh current I sub B. So we take the value of I sub B, multiply it, put it here, and you get an output which is equals to this one. So from here, we can get the ratio v sub O over v sub I, so which is our transfer function, and we'll actually get 5 over s squared plus 8s plus 5, which we can factor out as two factors and bring the value of s, which is j omega. So we'll get something like this. So at this point, we can say that our n of omega is equals to 5, and the omega is the denominator of the transfer function. So since the n of omega is a constant, we'll have no zeros. And for the poles, we have 2 because we have two factors for the omega. So that would be p sub 1 negative 0.6834 and p sub 2 negative 7.317. We can get the magnitude with transfer function. So this is the magnitude. And we can do the same for the phase angle. Then we plot the magnitude. So as you can see, the magnitude of the transfer function varies from a maximum when omega of the input is a 0, we get the transfer function equals 1. And this decreases as omega increases. For the phase angle, it is a 0 if omega equals 0, and it decreases as the omega increases. Okay?